I've been introduced already, so I won't repeat that, but my name's Erin LeDell, and I am a statistician and machine learning scientist at H2O. And this first talk is going to be pretty introductory, so it's geared towards people who are new to data science and people who have, already installed H2O and are not busy with that. So I will continue. The first two slides are just the app. So if you haven't downloaded the app and you want that on your phone, it has the full schedule on there. That's where you do that. And then these were mentioned already, but the stickers, if you go to the installation booth or information booth, and you can pick up stickers and assert that you have done all of these steps. Okay, so this is the overview of the talk. So I'm going to start out with what is data science, at least in my opinion. And I'm going to talk about what a data scientist is and what does that term mean. And the data science team and how that's different from sort of the unicorn data scientist. And then I'm going to talk about data science tools, and then a few more things. So what is machine learning, what is deep learning, and what is ensemble learning? So those are all just different types of machine learning, deep learning and ensemble learning. And I will talk about some of the just general concepts like cross-validation, train and test, that type of thing as well. And then I'll end with some data science resources that you can visit if you want to learn more. Okay, so what is data science? It's a term that we use these days, and as far as I can tell, the first use of this term was in 1996 at this conference in Japan. So the International Federation of Classification Societies, which is, I guess, a yearly conference that they hold in Japan, and at least according to the internet, that is the first utterance of that word. Could be earlier, but that's what we think it is. So it's been around for quite a while, but only recently become popular. So how did it become popular? So in 2001, there was a paper called Data Science, an Action Plan for Expanding the Technical Areas of the Field of Statistics. So this is written by somebody named William Cleveland, who was at Bell Labs. And so what he noticed was that there was sort of this new science that was emerging that sort of pulled from all these different directions and was not really limited to one like academic discipline. And so he sort of laid out this plan for how universities should try to tackle this. So I know that at least at Berkeley, this is the first year they actually have an Intro to Data Science course. So I think it took 15 years to get there, but you'll start seeing that at universities, having specifically data science courses, and even things like a data science master's. So it's taken a while to become sort of official, but I think we're there now. Okay, so just like I said, data science is just a term, so I'm just showing sort of the trend of the term over time. So in blue, we see it sort of spiking. Maybe, I guess in 2013, maybe that's, I don't know, when it started to go up a lot. So machine learning kind of increased at the same rate. Predictive analytics is kind of a little bit older term, so that's kind of stayed constant. And I guess it's not as exciting of a term, so people don't say it as much. All right, so this is sort of my 3 bullet point description of what data science is. So I like to kind of break it up into 3 groups, or 3 steps, I guess. So the first step would be problem formulation. So this is probably the most important step, is sort of clearly defining what it is that you're trying to do. So are you trying to make some sort of prediction? And if so, is that a numeric prediction? Is it a classification? Is it a ranking? So defining what it is that you're trying to solve. And so from the very beginning, then you kind of work backwards towards figuring out what you need to solve that problem. So also, I think in the problem formulation, you can consider collecting the relevant data. So once you decide what it is that you want to predict, you probably start to think about, well, how would I predict that? What other data is out there that I can collect? that would be sort of correlated to that response. So once you have collected all this data, this middle step is probably a huge portion of your time. So, we're getting more tools to make this easier, and that this part will sort of become less of your time, hopefully, as the tools become more sophisticated. But this section contains cleaning, transforming, filtering, aggregating, any sort of data munging basically goes into this step. So usually the goal, if you're doing sort of a standard prediction problem, is you want to end up with a matrix that we'll call X, and a column or columns, depending on how many different things you're trying to predict, called Y. And so in X, basically the rows are your training examples. So and then the columns are your features or your predictive variables. So once you might start with text data or unstructured data or log data or something like that. The goal is to convert that into this XY framework. And X is also sometimes called the design matrix. And once you've made it that far, then the last thing that you would have to do is then perhaps train some machine learning models. There's a lot of different ways to do that, and I'll talk more about how to think about that process at the end of the talk. So once you've trained the models, you also have to be able to evaluate them, and then sort of the part that's missing from here is then once you have this set of models, then you might want to take them to production or something like that. So that's, I guess, the fourth hidden point here. Okay, so I think no data science talk would be complete without this Venn diagram. So this is kind of popular on the internet and elsewhere. So data science, according to Drew Conway in 2010, is sort of the intersection of all of these particular things. And maybe you find yourself fitting into one or more of these categories, maybe somewhere in the middle. It's just kind of a nice viewpoint of what data science is and sort of the three main skills that you need to have to be an effective data scientist. Okay, so this is another image I found on the internet. So this is sort of the ideal data scientist. So somebody who has all of these skills. So someone who has maybe a math and statistics background. They also are a programmer and know how to use things like Hadoop and MapReduce, Hive, Pig, Python, SQL, all of that. This is sort of a tall order to fill, but that also requires you to have some sort of domain knowledge. If you're, let's say you're using image data, maybe you need to know a little bit about how to process images and that type of thing. So the last section is the communication and visualization section. I would say that it's pretty hard to find somebody with all of these skills. The people that do have all these skills probably have already started their own companies, and you can't hire them. They're too expensive. So you should just sort of, this is sort of a dream of a couple years ago that we would find these people, and they were just a matter of searching on LinkedIn enough to find them. But really, these people are very rare, and so that's why they're sometimes called the data science unicorn. And so I guess there's a Twitter handle called Data Science Unicorn, which I thought was pretty funny. So the idea is that these fictitious creatures exist only in places that you can't find them usually. So this is just sort of a slide about, so I mentioned LinkedIn. So there was a survey of data scientists on LinkedIn by a firm called RJ Metrics. And I think this is from 2015. So the number of data scientists has doubled over the last 4 years. So that's, I think I read still that there's maybe only like 10,000 people who identify as data scientists. I don't know if that actually matches up with what the survey says, but there's a number of different surveys that try to quantify the number of data scientists. And so here's the top 5 skills, at least according to LinkedIn, or data scientists who have a LinkedIn profile. So 1, data analysis, 2, R, 3 Python, 4 data mining, and 5 machine learning. So, okay, so I think in the last year or two, people have sort of moved on from this idea that they want to find this data science unicorn, and they're going to hire them, and then they're going to be able to do all of the work. And I think what we've started to realize is that that's great if you can find those people, but really it's probably more effective to try to hire 2 or 3 people or a whole team that has some of these skills and has maybe a database person or a data engineer type person, a visualization person, a scientist. So all these people coming together are actually more common, I think, in industry. Although there are some companies that just hire the magical unicorn, and sometimes that works out, sometimes it doesn't. So I would say give up on the unicorn idea and try to assemble a team if you can. Okay, so how would you assemble a team like this? So, these are just 3, again, just names that are kind of vague, but this is kind of how I see data science teams. So there's data analysts. So that word could also describe a data scientist. It's pretty generic, I guess. But so a data analyst would be somebody who has strong quantitative abilities and also is good with using the existing data tools. So if you're somebody who maybe can use scikit-learn or something like that, but you don't know how to actually implement algorithms, maybe that's more of a term to describe you. So the other thing that I think data analysts are good at are the ability to tell a story with data. So if you can kind of interpret a whole data science pipeline and be able to describe that to a client or that type of thing. So then the second category would be data engineers. So these are more of your CS or engineering types. And again, this is just another term, assuming you have enough people to sort of distinguish among these abilities at your place of work. So this would be somebody who's very good at DevOps type of things. So maybe they're good at setting up a Spark server or Hadoop or something like that, and they work on more of the data processing, pipelining type of things. And then there's the data scientist. This is more of a math or stats person who can also write code. So, and somebody who has at least some fair understanding of machine learning algorithms, enough to sort of know which ones to use and know if you're using them correctly and know how to evaluate models. So that's just one person's opinion of a data science team. Okay, and so here's just another Google Trends plot about these 3 terms. So I was kind of surprised that data engineer is not as popular as I thought it would be, but maybe that's more of a new term. So data analysts and data scientists, I think, are very similar. Okay, so how do we bring this stuff into the enterprise? So what do these teams do? So they, this is a term that you hear all the time, actionable insights. I've heard it so many times that it, I kind of laugh when I hear it, but I think I would like to get like a T-shirt that says actionable insights on it and wear it around. But so that's sort of what we do. It's a good term, and it's used a lot because it's very succinct definition of what you provide as a data scientist. So you're providing information that can then be used to make decisions, essentially. So if you're just sitting at your computer, calculating the AUC of a model, then that's great. But what are you going to do with that? Is that going to save money somehow or make decisions in some way? You really need to be able to translate that science into something useful. So there's a lot of places that data science can be used in the enterprise, and over the next 2 days, you'll hear a lot about our customers and how they're using at least H2O in the enterprise. So the obvious thing is that you get a competitive advantage if you're using data science, because there's usually, there's just so many ways that you can sort of beat out your your adversaries by having better data science. And one of the more direct things is cost minimization. So that's usually where people start, is there's some process that could be improved upon by using data, and usually the intent is to save costs in some way. And sort of the third bullet point is you can create new products that didn't exist before. So, that's a whole nother domain. And there's whole companies that sort of have created data-driven products. Okay, so I found this cartoon when I was searching around for images, and I thought it was kind of funny. So here's sort of the state of things. So the cartoon reads, "We can't compete on price." And he says, "We also can't compete on quality, features, or service." And he says, "That leaves fraud, which I'd like you to call marketing," which it's kind of funny. And I'm not trying to be mean to marketing. But what I'm saying is that you're going to have to pay to get your product out there somehow. So you can either make it better using data, or you can use all of your money to use for marketing. So the best would be the combination of both. Make a really good product, and then be able to beat out all the competitors because you have a better product and you don't need to do as much marketing. So my thoughts on that are don't be a data dinosaur. Embrace the data. Okay, so next, data science tools. So I don't know if you guys noticed this, but this is something that I noticed in the last couple of years. There's been tons of articles on what's the better tool for data science. Is it R? Is it Python? And there's all these fights on the internet about it, and all these articles. So when I was searching for this, it seemed like all of the articles, or at least a lot of them, were written in 2013. So I don't know if that was just a coincidence, or if that was sort of the mantra at the time, and that because now I think in 2015, I'll say we've sort of moved beyond this, where if you're a data scientist, and let's say there's a lot of data scientists on Twitter, and they talk about these type of things all the time. At least I've noticed that the new mantra is that if you're still fighting over which language is best, you're missing the point. So we're all going to move on, I think, now, and just agree that each language is good for its own things, and you should just choose whichever one you like. I mean, I guess the only time this question is useful is when you're first starting out and you do actually have to make that choice. So it's still an interesting discussion to have, but I think there's so much drama about which tool and all these surveys and stuff like that. So anyway. So it's 2015 now, and it's time to move on. So we have these things, I don't know what they're called, but you can stand on them and run around now. So this is the future, really. Okay, so here's some data science tools. So at least in my opinion, I think we're sort of headed towards rather than sort of locking yourself into a language and what the software in that language provides. So it used to be this very big division between, are you building your data science stack in Python, or are you building it in Java, or are you, dangerous enough to build it in R completely? So it used to be kind of locked into one language. And I think what I've noticed is that there's a lot more tools now that sort of separate the data processing engines that are maybe written in a high-performance language like Java or C++ from the actual front end, which could be Python or R, or any language you choose. I think that's sort of the place that we're headed, and I think that's sort of what H2O tries to do. Okay, so I said I would define a couple more terms. So what is machine learning? So this is, if you look on Wikipedia, this would be the definition they would give you there. So this is the first sort of definition of machine learning. So the field of study that gives computers the ability to learn without being explicitly programmed. So the key difference there is, unlike rules-based systems that require a human expert to code in that domain knowledge, a machine learning algorithm will just learn from the data on its own. And it's helpful to have a domain expert in your team, but that's no longer required. Okay, and then just if you're new to machine learning, this might be useful. So just a couple different things that we do in machine learning are the different tasks, so different problems that you're trying to solve. So regression is where you're predicting some sort of real valued response. So maybe the price of something, or an example in medicine is viral load. And so these response variables have different distributions, usually Gaussian, gamma, Poisson, there's a number of them. And then another thing that you should be aware of is that for each of these different tasks, there's some set of evaluation metrics that are sort of more appropriate for that task. So if you're doing regression, you might consider evaluating your model with mean squared error, or R squared. And so it's good to be aware that certain metrics sort of go along with certain tasks. So the next group is classification. So this could be binary classification or multi-class. Sort of, I guess, as a subset of this, or a subset of binary classification, is something called ranking. So if your goal is not to actually classify things into groups, but to maybe just get a score of some sort, or ranking. So Google search results would be an example of that. So what order do we want to list those results in? And so some of the metrics that might be used in the classification domain are classification error. So that's if you're actually making your goal is to predict the label for the class, or maybe AUC, or area under the curve, if you're doing binary classification with sort of a goal of ranking. And I mean, there's certainly a huge, broad list of different machine learning tasks other than the ones that I'm listing here, like anomaly detection or things like that, but these are kind of the main ones. So the last, what I would consider main task, is clustering. So this is, and the type of clustering I'm talking about here is unsupervised learning. So that means that you don't actually have training labels, and your goal would be to partition the data, or sort of group people or rows, or whatever your training examples represent, into groups. And so these are some of the metrics that you could use to evaluate how well you've clustered your data. So AIC, BIC, or total sum of squares. Okay, so I'm going to just talk about a few concepts in machine learning. So one thing is to partition your data, and to understand that there's something called a training set, a validation set, and a test set. And I think the thing that people get wrong most often is not understanding the difference between a validation set and a test set. And sometimes people use those words interchangeably, which adds to the confusion. But essentially, a test set should only be used once. And you should, after you do all your training and model tuning, that should be the last thing that you do, is test on a test set. Validation sets are used for when you're actually tuning your models. And so you can use the validation set more than once. Then there's something called k-fold cross-validation. So this is another way, similar to the test-train split, that you can evaluate your data. So it's essentially breaking your data up into chunks, and repeatedly, in a structured way, learning on some set of those chunks, and then testing on the left-out chunk. Here's just a picture of sort of a typical machine learning workflow. And the point of this picture here is just sort of to break it up into two pieces. So there's a training phase. That's when you're training your models. And once you have your models set up, you have the prediction phase. So I'm supposed to start QA right now, but I'll take one more minute to sort of finish out the slides. So I just wanted to mention a couple of subsets of machine learning. So deep learning, which Arno mentioned earlier, is sort of one popular thing right now. So the thing that I'll mention is, why is it called deep? It's because there's more than one hidden layer in their architecture. And so these are popular for things like images, video, and audio. These deep architectures have been around for a long time, but some of the computing breakthroughs that we've had recently, as well as some of the math has evolved a little bit as well, have made these very effective as of late. And then the last thing is ensemble learning. I'm giving a talk about that later today. That's combining a bunch of different models together to sort of form a much stronger learner. And random forests and gradient boosting machines are examples of that, also stacking. And then my last slide is sort of this emphasis that there's no free lunch. So the idea is that there's not going to be one algorithm that works best all the time. And so that's sort of why we have all these different algorithms. And I will end there. Here's where to learn more. And I'll leave that up during the QA. So.
Yeah. Hello. Before I start the Q&A, just want a show of hands of who all have installed all the things you need for the hands-on. OK, so there's still a bunch of people who are still installing. So I would encourage all of you to get all of our hackers, get it installed, because the next session, which starts in 5 minutes, will be a hands-on session. So while we're doing the Q&A, please continue to keep installing, and our hackers help them out. OK. I'll walk around the stage for any questions, if anyone has. No. OK, no question. OK.
So it looks like people are raising their hands for installation, but probably not.
So we might actually bypass the quick Q&A for this session so that we can all get installed. So we got a few more minutes to get installed. So we'll wait for 5 more minutes, and then we'll. Thanks, Erin.
Yeah.